we will first see the minority carrier concentration profiles for different BJT operating regions. The dashed line represents the equilibrium minority carrier concentration. You should know for a forward bias junction, the minority carrier concentration at the junction increases, whereas for reverse bias junction, the minority carrier concentration decreases. Consider a random concentration profile of BJT and focus on the concentration of minority carriers at the two junctions. For the emitter junction, we can clearly see concentration of minority carriers are greater than the equilibrium concentration. Therefore, emitter junction is forward biased. Similarly, for collector junction, minority carrier concentration is smaller than their equilibrium values. Therefore, collector junction is reverse biased. So we can conclude this concentration profile of BJT is of active region. It should not be difficult for anyone to determine the operating region by just looking at the concentration profile. We can draw concentration profile for other operating regions as well. Saturation region is further divided into two cases. One, when forward bias voltage of emitter junction is greater than forward bias voltage of collector junction. This is referred as forward saturation region. And the other condition is when the forward bias voltage of emitter junction is smaller than forward bias voltage of collector junction. This is referred as reverse saturation region. Now we can begin our current analysis. For that, consider the two cases. Case 1, when the base is too long that it is no longer a BJT. Two PN junctions are considered to be connected back to back. The second case is when the base is very small, making it a practical BJT. However, in both the cases, the current through the emitter terminal does not change. So, we can find the emitter current assuming it is a terminal of PN junction. Like for ideal emitter based diode, we have emitter current equal to reverse saturation current of emitter based diode multiplied by exponential emitter based voltage divided by thermal voltage minus 1. We can also include the ideality factor if it is provided. After finding the emitter current, we can find the collector and base current also by using current gain parameters. For example, from the above relations, we will get the collector current equal to common base current gain into reverse saturation current of emitter based diode into exponential of emitter based diode divided by ideality factor into thermal voltage minus 1. Therefore, we can say collector current is directly proportional to emitter base voltage, at least for active region. We generally consider the active region as we get the best value of current gain parameters in the active region. By the same analysis, we can find current for three regions: active, saturation, and reverse active region by using respective current gain parameters as they will differ for different regions. However, for cutoff region, we simply consider the current values to be approximately equal to 0. For a normal PN junction, we know the value of reverse saturation current. If the N region is very small, even smaller than minority carrier diffusion length, then after short diode approximation, we can replace minority carrier diffusion length with width of the N region. Now consider a PNP BJT where collector is kept open. In this case, the reverse saturation current of emitter based diode can be written as. The second term can be ignored as the emitter concentration is significantly greater than base concentration and the diffusion length of free electrons is also greater than base width. Therefore, reverse saturation current for emitter based diode can be approximated to magnitude of a charge on an electron multiplied by cross-sectional area into diffusion length of holes multiplied by square of intrinsic carrier concentration divided by base width into doping concentration of base. Similarly, reverse saturation current for collector based diode can be written as. Here also, we can ignore the second term because collector concentration is significantly greater than base concentration and also diffusion length of free electrons is greater than base width. Therefore, reverse saturation current for emitter based diode comes out to be approximately equal to magnitude of charge on an electron multiplied by cross-sectional area multiplied by diffusion constant of holes into square of intrinsic carrier concentration divided by base doping concentration into base width. Therefore, we can say reverse saturation current for emitter based diode and collector based diode are approximately the same. However, they are not exactly the same. Now we can find the standard equation for emitter current by ignoring the -1 and replacing emitter base reverse saturation current with collector base reverse saturation current. We can find the currents from the magnetic area concentration profile as well. Here again we are considering the concentration profile for active region. We know diffusion current is equal to magnitude of charge on an electron into cross-sectional area multiplied by diffusion constant into gradient of hole concentration. For simplicity, we take a linear decrease in concentration profile from its maximum value at the emitter junction and becomes 0 at collector junction. You can see the emitter current is same in both the ways we tried to calculate manually from current equation of PN junction as well as from concentration profile. When we were solving manually from the current equation, we have seen what terms we have neglected to make it approximate current rather than exact current. Similarly, if we have to calculate the exact current from concentration profile, then we have to consider all the three gradients present in base as well as in collector and emitter. But that is generally not required because the other gradients or currents are very small. The thing is, the concentration profile which we see is meant for clear representation of data. But if we take it too literally, then it would look like this. Obviously, such concentration profiles are not preferred for proper representation of data, but you can clearly observe gradient of base is very large compared to gradients of emitter and collector.